So today we are going to start a new module, electrochemistry. So what do you mean by electrochemistry? So electrochemistry is a separate branch of science or chemistry which deals with electrons. So donation of electrons or receiving electrons. Okay. So electrochemistry is a separate branch of chemistry which deals with donation, giving and taking of electrons. So what are electrochemical cells? What is the example for this? We have two types of electrochemical cells. What is oxidation? What is reduction? What is redox reaction? What is electrode potential? What is standard electrode potential? What is the reason for electrode potential? What is entropy? What is free energy? These are the basic definitions. We'll discuss these today in our class. Okay. Electrochemical cells are the devices Electrochemical cells are the devices which convert electrical energy into chemical energy and vice versa. So the devices which convert chemical energy into electrical energy are called as galvanic cells. So there are two types of electrochemical cells. The first one is galvanic cell and second one is electrochemical cells. So electrochemical cells are divided into two types, galvanic cells and electrolytic cells. So galvanic cells are the cells where chemical energy is converted into electrical energy. So when you're using your battery, when you're using your phone, mobile phone, so you have a phone, and if you're using your phone, so the chemical energy is stored in that. So normally the energy used, battery used is lithium battery, right? So the chemical and electrical energy will be stored in the form of chemical energy, right? Lithium ions. So lithium ions will convert into lithium will get converted into lithium ions. So and it gives electron. That electron will be used for functioning of various apps in your mobile battery, right? So that galvanic cell where chemical energy is converted into electrical energy. Okay, electrolytic cell. So electrolytic cells are the cells where the electrical energy is used to bring about some chemical changes. So by virtue of electrical energy, when you apply some electrical energy or electrical current, some chemical changes can be brought about. So this is an example for, this is electrolytic cell. So example for your galvanic cell is your Daniell cell. Example for your electrolytic cell is your electrolysis process. Okay, so let us take an example of Daniell cell and see what are the reactions occurring in your Daniell cell. Okay, so here the Daniell cell consists of zinc dipped in zinc sulfate, copper dipped in copper sulfate. So Daniell cell, zinc is dipped in zinc sulfate, copper is dipped in copper sulfate. This both zinc and copper both are connected. Zinc and copper both are connected through a salt bridge. So this is a salt bridge over here are connected in order to maintain electrical neutrality. Zinc and copper are connected through a salt bridge. So zinc electrode and copper electrode are connected through voltmeter in order to measure the electrode potential. So zinc dipped in zinc sulfate, zinc electrode dipped in zinc sulfate, or any metal electrode dipped in its own salt solution is called as an half cell. Any metal dipped in its own salt solution is called as an half cell. So I have two half cells, that is zinc half cell and copper half cell. So zinc half cell and copper half cell are interconnected to the salt bridge. Okay, so when these two are interconnected to a salt bridge, so we have two electrodes over here, zinc electrode and copper electrode. At zinc electrode, zinc undergoes oxidation to give you Zn2 plus and 2 electrons. Zinc undergoes oxidation to give you Zn2 plus and 2 electrons. So these 2 electrons will move towards the cathode. Okay, so here at the cathode electron CuSO4, whatever is present, it will be in the form of Cu2 plus and SO4 2 minus. So all this Cu2 plus will be here. The positive charges will be near the cathode over here, electrode over there. Okay, so as soon as the electrons comes over there, the Cu2 plus will accept the electrons and gets reduced. So how it will get reduced? So Cu2 plus will accept two electrons to give you Cu. Okay, so zinc at zinc electrode, zinc undergoes oxidation to lose two electrons, that is zinc is giving you, so you have zinc electrode here, it is losing two electrons to give you Zn2 plus. This is called as oxidation. So if a metal accepts any electrons, it is called as reduction. So in general, loss of electrons is called as oxidation, gain of electrons is called as reduction reaction. So zinc undergoes oxidation whereas copper undergoes reduction. So this reaction continues until zinc is dipped in zinc sulfate solution or copper is dipped in copper sulfate solution. So any one of these goes, then this reaction will not occur. So when these two reactions, this oxidation and reduction reaction occurs simultaneously, it is called as redox reaction. Okay. So now we have, as per IUPAC, so the electrode where oxidation occurs is called as anode. So where oxidation occurs? At zinc, oxidation occurs, isn't it? At zinc, what is occurring? Oxidation is occurring. So therefore, it is called as anode. At zinc, oxidation occurs, and it is called as anode. And at copper, what reaction is occurring? Reduction reaction is occurring. Therefore, it is termed as cathode. Okay. So here, in all your galvanic cells, zinc acts, anode is negatively charged and cathode is positively charged. So remember this very well. So all your galvanic cells, anode is negatively charged and cathode is positively charged, right? So whereas in a electrolytic cell, it is different, it is opposite way. Whereas in your galvanic cell, anode is negatively charged and cathode is positively charged. Okay, so why is this? Let us see. So let us consider zinc dipped in zinc sulfate solution. We have zinc and it is dipped in zinc sulfate solution. So what happens? Zinc undergoes oxidation to give you Zn2 plus and 2 electrons. So these Z2 electrons will be on the surface of electrode over here, as Zn2 plus will be in the solution. Since all the electrons on the surface over here, the electrons or negative charge will attract the positive charges over here. Forget it. So the electrode gets a overall negative charge, and this because of that, anode is negatively charged. Okay, so zinc undergoes oxidation liberating Zn2 plus and 2 electrons. Zn2 plus will go in the solution, whereas electrons will be on the surface of the electrode, giving the overall negative charge. So whichever electron undergoes oxidation, same thing will appear. Therefore, anode is negative. So whereas cathode, reduction occurs. So at cathode, all the positive metal ions will be waiting for getting electrons, right? So it will be here. So all Cu2 plus will be surrounding the cathode. Therefore, it gets overall positive charge. Got it? So we have, so anode is negatively charged, cathode is positively charged. At anode, oxidation occurs, and at cathode, reduction occurs. So how do you represent a cell? So we have here, this is a cell representation. This above cell, whatever you have here, it is represented by this. So the two lines, whatever you have here, this is your salt bridge. This salt bridge is represented by the two vertical lines. So left hand side of salt bridge is anode and right hand side is your cathode. So at zinc, what happens? Oxidation occurs. So write that Zn slash ZnSO4. So write Zn. So what is that? Zn gives Zn2 plus 2 electrons, right? So here what do you do is write that Zn, this Zn here, instead of arrow mark, put a slash and write Zn2 plus. So it's not necessarily supposed to write the electrolyte, can write this. Okay. Similarly, right hand side, we're going to write the other reaction. Okay, Cu2 plus, okay, slash Cu. So this is the representation of your Daniell cell. Okay, so in general, in any chemical cell, in any cell, galvanic cell, anode is negatively charged, cathode is positively charged. So what is oxidation? Oxidation is loss of electrons and reduction is gain of electrons. So remember this properly. So next, let us see what is electrode potential. So electrode potential, it is nothing but whenever a metal is dipped in its own salt solution, it has a natural tendency to either lose electrons or gain electrons. So due to which metal gains a potential which is known as single electrode potential or just electrode potential. So this electrode potential is given by E, okay, represented by E. So let us understand why a metal gets potential. Let us take the example of zinc itself. So zinc is dipped in zinc sulfate solution. So what happens? You have zinc, and what happens as soon as you dip zinc in zinc sulfate, what reaction occurs? Zn undergoes oxidation to give you Zn2 plus and 2 electrons, isn't it? So this Zn2 plus will go into the solution over here, whereas electrons will be on the surface of the electrode. You know this. I already explained this. So because of this, the electrode gets the overall positive charge. So these electrodes or these negative charges will not keep quiet. What it will do, it will attract the positive charges. So these positive charges will come here and sit here, okay, next to negative charges. So it seems as if the overall electrode is covered with two layers of charges. So there is some type of attraction between negative and positive charge, that is called as, when you take I think most of us would have played what with magnets, isn't it? Negative and positive in childhood. When you take north pole and north pole, it will repel. North pole and south pole, it will attract. So when you take north pole and north pole, you can feel the magnetic force of repulsion. So similarly, this positive and negative will not attract. So there is some force of attraction. That force of attraction put together is termed as electrode potential. This entire thing is measured at standard temperature, standard pressure, and at 1 molar concentration. It is called as standard electrode potential, and it is given by E naught. It is given by what? E naught. Okay. Yes. So next. So there are a few things which is very important. So the few definitions. Free energy. So what do you mean by free energy? So you have to take any substance. So energy is associated with almost all substances. So it might be internal energy or external energy. So energy which can be converted into usable form is known as free energy. So usually energy is given by, free energy is given by G. That is free energy is given by G minus G equals H minus Ts. So if it is free energy, if change in free energy means delta G equals delta H minus T delta S, where G is change in free energy, delta H is change in enthalpy, delta S is entropy, right? So if delta G is 0 for any reaction, then that implies that the reaction is in equilibrium. If this delta G value is negative, then implies that the reaction is spontaneous. If delta G is positive, then the reaction is non-spontaneous. Okay, so this value itself decides whether the reaction is at equilibrium or at spontaneous or non-spontaneous. Okay, so similarly we have entropy. So what do you mean by entropy? Randomness. So it's a measure of randomness of a system. So we'll understand better by looking at the video. What is entropy? So in general, if if entropy is 0, entropy is 0 for almost all reversible process, and entropy will be greater than 0 for irreversible process. Okay, so randomness or disorderedness of the system is called as entropy. To understand better what is entropy by looking at this video. There is a small video over here. Just look at this. What is entropy? To understand better.
There's a concept that's crucial to chemistry and physics. It helps explain why physical processes go one way and not the other, why ice melts, why cream spreads in coffee, why air leaks out of a punctured tire. It's entropy, and it's notoriously difficult to wrap our heads around. Entropy is often described as a measurement of disorder. That's a convenient image, but it's unfortunately misleading. For example, which is more disordered, a cup of crushed ice or a glass of room temperature water? Most people would say the ice, but that actually has lower entropy. So here's another way of thinking about it, through probability. This may be trickier to understand, but take the time to internalize it, and you'll have a much better understanding of entropy. Consider two small solids, which are comprised of 6 atomic bonds each. In this model, the energy in each solid is stored in the bonds. Those can be thought of as simple containers, which can hold indivisible units of energy, known as quanta. The more energy a solid has, the hotter it is. It turns out that there are numerous ways that the energy can be distributed in the two solids and still have the same total energy in each. Each of these options is called a microstate. For 6 quanta of energy in solid A and 2 in solid B, there are 9,702 microstates.
Microstates.
Of course, there are other ways our 8 quanta of energy can be arranged. For example, all of the energy could be in solid A and none in B, or half in A and half in B. If we assume that each microstate is equally likely, we can see that some of the energy configurations have a higher probability of occurring than others. That's due to their greater number of microstates.
So the entropy changes from solid to liquid, liquid to gases. So ice has less entropy, water has more entropy, and gas has greater entropy. This is just for understanding. This is further studies. Okay. Thank you. We'll meet in our next discussion with Nernst equation, how to derive Nernst equation. Okay. Thank you.